All right, so we're going to find the equation or equations of the line or lines tangent to this curve on the x-axis. So if it's on the x-axis, where is that, guys? Y equals 0, right? On the x-axis means y equals 0. So first thing we want to do is find any points where that's true. You guys can talk in the room. So if I plug 0 in, then what do we get? 3x squared plus 5x. Cosine of 0 is 1, right? Equals 0. So 3x squared plus 5x equals 0. Solve for x, right? So x, 3x plus 5. We get x equals 0 or negative 5/3. Look good? Cool. So those are the coordinates, the x-coordinates for the zeros, for the x-intercepts for this curve. I was going to say function. It's not really a function, though. Usually when you have like x's and y's mixed together like this, we're going to get a weird graph. I'll show you in a minute. So our points, though, our points of tangency are 0, 0. So that's the origin. Looks like an owl. And negative 5/3, 0. And so that's what we're going to work with. All right. I'm going to go ahead and just like kind of do each one separately. First, though, we do need the derivative, right? Here, I'm going to put this off to the side. So derivative. We're going to use implicit differentiation because we have x's and y's mixed together. There's no good way to isolate y. So differentiate with respect to x because we want the slope of the tangent line in the xy coordinate plane, right? We want change in y over change in x. And that's what dy dx is. It's a change in y over a change in x, or a ratio of that. So we're going to differentiate with respect to x. And you don't have to write that when you're doing it, but I'm just being thorough, showing what we're doing to both sides of this equation. Derivative of 3x squared, 6x. Derivative of 5x cosine y. Did you guys all do a product rule there? Cool. Got u, and we've got v. So I need u prime v. U prime is 5 cosine y plus uv prime. So it's going to be 5x times negative sine of y. So I guess I may as well put the minus right there now. 5x sine of y. What am I missing? Y prime or dy dx. Good. I'll put parentheses there so that it's clear the sign ends. And then I still need the other side of this equation, which was the 2y cubed. Do the power rule on that. So it's going to be 6y squared, y prime, dy dx. Perfect. I'm going full Leibniz here with the dy dx. All right. Just keep everything positive if you can, right? We'll bring this term over, factor out the dy dx. So that's going to look like this. Dy dx, I had a 6y squared, and I'm adding over the 5x sine y. And on the other side, I've just got 6x plus 5 cosine y. And I want to solve for dy dx, so I'm just going to divide both sides by this junk in the parentheses here. Jump in if I do something dumb. I'm just going to kind of do that. All right. And I've got my dy dx. And that's what I'm going to use for the slope. My 2 points are 0, 0, and negative 5/3, 0. So I'm just going to go ahead and let's see. 0, 0, and negative 5/3, 0. So if I plug 0, 0 in, I think this is going to be a little bit of an issue here. Oh, no, we're good. Okay. If I plug 0 in, we're going to get 0 plus 5 times 1 on top, right? 5 times the cosine of 0. On the bottom, we're going to get, well, there's a y here, and then sine of y. When you plug 0 into that, you're going to get 0 for both of those terms. So we're actually going to get 0. That's 5 over 0. That does not exist, right? That's undefined. Talk about what that means in a second. The same thing is going to happen over here because this also has 0 for y. So that denominator is going to do the exact same thing. Doesn't really matter if we plug negative 5/3 in for x. We're going to get, what's that, negative 30/3, so negative 10. plus 5 on top, and we're still going to have 0 on the bottom. And so also undefined. Okay, by the way, this work that I'm doing, if I was trying to label it, which would probably be a good thing to do, I would write this Leibniz notation, dy dx, with this line here, and then say at 0, 0. That's how I would label this work. So I'd say like m equals this equals that. And the advantage to the Leibniz notation here is this isn't a function. So I can't really use function notation, right? I can't be like f prime of 0, right? So because I have to plug both x and y values in, this notation is really handy. The rate of change of y with respect to x at the point 0, 0. And it's a pretty standard notation. They use it a lot for AP exam scoring rubrics. They like it. So I recommend it. Anyway, both of those lines are going to have an undefined slope. So what kind of a line is it? Vertical, that's right. It's going to be a vertical line. And so it's through both of those points. So this one's x equals 0 because that's the x coordinate here. This one's going to be x equals negative 5/3. And so that's it. Those are our two tangent lines. Kind of a little anticlimactic there because they're pretty easy equations to write. But if we look at the graph, sometimes it does go that way. If we look at the graph of this function, you can see that at those two zeros, it does kind of look like there might be vertical tangents, right? And here, if we type in, well, let me do it here. Here we go, keyboard. So we do x equals 0 and x equals negative 5/3. And yeah, you can see the tangent there with that green line at the point on the x-axis. And there's also the blue tangent line there. It does pass through the curve there, but the curve does have a vertical tangent for an instant. Look good? Awesome.